Hello everyone and good morning. So today we have a very awesome speaker, Abhijat Vichare. He conducted computer simulation on HPC system of atomic cluster to study the melting transition for his doctoral work in physics. As a faculty at the Department of Computer Science, University of Pune, he taught programming languages, system software, operating system, etc. At the Department of Computer Science and Engineering at IIT Bombay, he was a research scientist working on the GCC system to unearth its architecture given the implementation. Subsequently, he has been a senior scientist at the Computational Research Laboratory, now part of the TCS, where he worked on the ECA supercomputer to perform simulation in physics and develop workflow for other application domain like biology and CFD. Currently, he offers his service in system software and compilers. His general interests are in theoretical aspects of computer science, particularly teaching. Yeah, Avijat, now you can enlighten us.
Thanks, Avanish and Subhajit, for this wonderful opportunity. I'm privileged. So, good morning, everyone. Wish you all a very, very happy new year. And let's hope that 2022 sees the end of COVID. And that's something that has been troubling. As some of you might have heard, I have been missing out the face to face interactions. But nevertheless, we are going to do the best with whatever we have. Um, Thanks for the introduction, Avnish. And in that introduction, I hope, I mean, you get an idea of the kind of work that I've been doing. My interests have been in computing and particularly system software. And what I'm going to share with you today are some of the ideas about runtime environments. You have in this school heard about the hardware side of the story, and we are going to assume some of that. In particular, we are going to assume a kind of a I won't say minimal, but bare bones, as is necessary kind of a view about hardware. But the idea is now to look at a kind of a bridge between hardware and software. What's going to occur? We all know that operating systems and programming languages actually form that bridge, and the actual connect comes at runtime environments. That is what we are really going to talk about in this and the next session to do together. There are some exercises coming your way that I hope you try it out later in the day and at even later at times also. Some of the exercises could be a little challenging, but let's go ahead and try to see what these runtime environments business is all about. There could be some aspects that some of you would be familiar, but I hope on the whole everyone gains something new out of these sessions. So let's get started. There are two sessions over here in this particular part, and in the first part, we are going to sort of try to understand what is this business of runtime environments, and we'll try to motivate ourselves by starting with what we want as a process and trying to think of what a program should be, and then also looking it forward from a program to a process. At this point, I'm going to assume that we know things about what's the distinction between a process and a program and stuff like that. But you're all welcome to interrupt me and ask questions about any issues that might be troubling you. Questions are always welcome, and I hope to stand up to your expectations through the answers. So the intent of session one is to really look at this idea of a tool chain and how the various tools really come together. Okay, having set the responsibilities of the entire business right, in the next session we look at this idea of creating executables and process and the runtime system, how all of these come together. And the key idea that I'm going to put forth here is the idea of binding. Okay. And there are some issues there that we will discuss. So this is the overall plan, and as I said, as we start session one, let's begin with looking at what we need. That is, we have a piece of hardware, and what is the kind of a view of a software that we need. That is what we are going to work backwards. And of course, when we actually practice it, we are going to do it the other way around. We are going to start from program to a process. All right. So session one is primarily going to focus on all of these things. Okay, let's begin the story. What we have in front of you is a kind of a sketch of the hardware and some bit of the software. There is a CPU which has some registers, CS, IP, DS, DX, SSSP, and so on and so forth. And the idea is to suggest that they are occurring in pairs. The CS, DS, SS are supposed to be the segment registers. We are assuming that our memory system supports segmentation and also paging, by the way. All right, and IP or DX or SP are the individual offset registers, as they are called. You have some view, there is some kind of a virtual memory that exists, and I'm going to divide that in frames. There are frames F0, F1, F2, etc. And then, of course, there is physical memory, which is going to be divided into pages P0, P1, P2, etc. At times, I'm going to represent memory again with a similar picture, but instead of frames or pages as a set of bytes, the memory will be individual bytes itself. All right, but we'll take that up when necessary. Otherwise, generally, we will be talking of frames and pages. As can be expected, the frames and pages are of same size. That is another implicit part. This is the stuff. And on the top right side of the slide, you would see two green rectangles, which are supposed to be representing the program bytes. Okay. One group is will be representing the code, which has S suffix C amount of bytes, and the other is a segment that we're supposed to represent data, and there are S suffix D subscript D, the subscript D amount of bytes. That generally is what is the scenario we are going to start with. And the hardware expects that whatever software we are going to have is going to be, must be correctly working on such a system. All right. And so the task of our task when we produce software is to produce it in such a way that it can be taken up by the hardware. All right. So let's see that. Let's start building that side of the story. This is how the program is expected to be. Okay, we have one code segment which has instructions which must be in binary. Binary because that's the typical technology, but what we are really looking at is some integers, some numbers. So these are your opcodes, and there are S subscript C amount of them. There is a data segment where each data type must finally be again represented in binary, and again, as I already said before, the number of bytes is S subscript D. This is what is expected by the hardware in terms as a program. Okay. In short, it's a machine language code. How do we really lay out this program in primary memory? Primary memory is the physical memory, of course, but then there is a virtual imaginary memory within which the allocations are first done. So the segments for code and data are allocated in virtual memory. All right. So I've sort of pictorially indicated that side of the story. The pictures try to indicate that the code that was there in the program has been loaded into the code segment. Some region of the virtual memory has been designated to hold the code, and some region of the virtual memory has been designated to hold the data. Okay. And then when the program runs, you also need some more parts called as the heap and the stack. How do you access them? Well, uh, I am hoping that the arrows are a bit visible on your machine. I can see that the contrast is not very good. So do excuse me, I'll try to work on them and set them up when I share these slides. But until then, I am hoping that you can see that there is an arrow from the CS register that is pointing to the start of the code segment. And the IP register points to somewhere in the code segment. Similarly, the DS register points to the start of the data segment, and the DX register is pointing to somewhere within the data segment. The SS register is pointing to the stack segment, the start of the stack, and the SP register is pointing somewhere in between. At this point, I must also say that the stack segment grows in the opposite direction as compared to the other segments. So the other segments start from the left and grow towards the right, whereas the stack segment starts from the right and grows towards the left. All right. So in principle, it's possible that the heap, which is supposed to be used for dynamic memory, can grow towards the right, the stack can grow towards the left, and there can, in principle, come a point where they sort of bang with each other, possibly intersect, intersect. So it's at that point we should see errors like heap allocation can fail or the stack can go for a toss and stuff like that. All right, but nevertheless, what I want to show here is that the way the memory is going to be used is like this. All right. We are also assuming that there is a paging infrastructure that is there. So all the data, code, heap, stack have been put in pages, and I have shown some kind of a page allocation over here. All right, that probably is consuming the entire memory. But the whole point is that there is a memory management unit, a hardware support for memory management provided to us. That's available. That's what I'm going to assume. Okay. To be a bit sharper, the actual allocations are like this. Only parts of the data, code, heap, and stack get allocated, and the rest of the allocations are as on demand. Okay, but that's a relatively minor issue. The point here being there is some expectation by the hardware because there are some rules according to which the hardware operates. All right. And this is the backdrop on which we are supposed to create our working programs. So let me sort of give a little detail, slight detail over here. For a moment, assume that the code has dynamic memory allocation instructions. So assume, for example, it was a C program where the programmer said that he or she wants to allocate memory dynamically using, say, malloc or calloc. And that code's instruction sequences are there in the code segment. Okay, the code segment has been allocated a page that you see over there. Okay, so those same instructions are there in that page, and it so happens that the CPU sort of executes them. Okay, When such a memory allocation request comes, typically it's actually going to be an OS trap. There's a system called trap to the OS memory manager, okay, which is who is really going to allocate some heap. All right, some memory on the heap part will be allocated using the OS memory manager. And once that pointer is set up, it comes back into some data, some variable. So the C programmer will typically write some variable becomes malloc, whatever amount of memory is required. So once the malloc system returns the pointer, it is then put into the variable, which we are going to assume is in the data segment. That is why that red arrow is taking you from the heap to the data segment. Okay. I thought of sort of giving this idea because I just want to bring out that there is a role of the OS in this entire story. That is, it's also there. We will see at a later point how this OS starts playing in this game. All right.
Hello.
Yes.
I was just curious, like, as far as I know, segmentation is not used in programs in like a decade or more. So, like, why are we expecting it? Like, is it still used?
No, I mean, the reason I sort of put it up is because your typical machines on the desktops, etc., do have that. If it is not there, then you will have to rework the entire idea accordingly. The whole point of the story is that there is something that the hardware gives you, and your entire execution or your entire program must be set up accordingly. That must be the final goal. All right. So if the hardware is giving you segmentation, then that's how you're going to set up your binary. If the hardware does not give you segmentation, then again, according to whatever rules the hardware says, without segmentation, that's how you will going to design your binary. That is how you need it. That is the point. Does that make sense?
Yes. And like just confirming those sections, the stack code heap, we are saying that those are one page long here.
They are one paged.
One page long for purposes
No,
of
no, 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 no. That is not what I mean. What I mean is that out of the entire segment, only one page has been allocated. Uh, it, Otherwise, the picture will be very messy. All right. That is one part. The other part is out of the entire segment, only those pages that are needed will be allocated. In other words, I am alluding to demand paging as a system, as a memory management support that exists.
Ah,
Right.
yes, right. Thank you. I
Yeah.
get it.
The idea is not that one single segment is put into one page. No, that's not the idea. Oh, okay. There is a visual problem here because all the segments seem to be having just the same amount of length, right? They seem to be visually occupying 3 frames. Okay. No, so please, I mean, the segments, I sort of happen to just copy paste them. That is why they appear like that. But think of the segments as having different sizes. Okay, please do that. Okay. Anything else? Okay, so let me go ahead. So the kind of expectations would probably be something like this, that if I were to summarize them, the program must be in binary form with all the non-runtime memory layouts defined. By non-runtime, I mean memory layouts like code and data, which is something that you can define before the program starts running. Whereas heap and stack are not something that you can define a priori beforehand. All right. These are segments that you can only that only will make sense when the fellow starts running. Okay, and the program must be defined in terms of the hardware architecture. That's what we just saw. I mean, we are assuming segmentation in this case, so we have to create the binary accordingly. If there is no segmentation, we have to create in that manner. I'm also assuming virtual memory here. There are systems where there is no virtual memory, and then you have to design your binary accordingly. You have to design it such that there is no virtual memory assumed. Okay. So uh, the point is the hardware offers a kind of a platform, kind of a base over which there is a program binary that you're supposed to create. Now you can have whatever high level language you choose from maybe an assembler or fantastic assembler like C or C++, Java, Java, Lisp and Haskell and whatever you want. Whatever be the language, it has to be reduced to what the hardware expects. The program in memory view, it has to be reduced to that. All right, that is the summary over here. That's something that we need to keep in our mind. This will have some impact on the idea of runtime, so we will see that a little later. Okay. So all of these expectations are summarized in this kind of a sentence. All compile time memory segments must, with binary contents, must be defined. All right. So all of these ideas are brought together into one single statement. Okay. All right. Now let's take the other view. But before I go ahead with the other view, any questions, anyone? There is one idea that we just discussed, and are there any questions anyone, if anyone has any? All right, so let's go ahead with the other side of it, so for other direction, from a program to a process. So we have a source program, binary program, and a binary program to a process. That's typically the two-level division in this, within which the view works. For concreteness, we have to assume that there is a compilation-based approach. So a file to a binary program. Okay. Important to idea of actually using interpret is not something that we are going to really look at, important than compilers. So here is the idea that we want to start with. We need to gradually transform our source program to its equivalent binary version in a way such that the target hardware plus operating system can execute the binary. All right. The alert for folks among you might have noticed that I've very subtly inserted operating system also into the game. So target hardware plus operating system is now the name of the game. We will see why that OS is coming up. I had promised this part a little earlier also, but here is one point where I'm just making it a little more explicit. But let's really look at the gradually transforming the source program to equivalent binary version. Now, this is a point that this part could be a little repetitive for many of you, but bear with me. Please bear with me. There are some ideas that I want to discuss, and maybe it's possible, I hope, that there is something new that you gain over here. But let's go ahead. Excuse me. So, I am going to assume again a very command line driven approach. Okay, typically that's what most Unix people, Unix, GNU Linux people do. And the universal compiler, in this case, is the GCC system. So uh, I am going to assume that most everyone is familiar with this idea of using GCC to compile C programs. And we use this command gcc myprogram.c and stuff like that quite often. What we are going to do is to peel off the onion and see what is inside. That may bring tears to the eyes, but that's what onions do. That's what peeling onions does. So let's go ahead and see what happens inside. The command that you give GCC is really what is called as a compiler driver, because internally it actually calls the true C compiler. So suppose GCC is working on some program called software.c, then the real compiler is the program called CC1, that is internally called by the GCC driver program. And C compiler translates the C program to assembly code, the target assembly code. So you have software.s, the assembly version of the program that you are compiling. The GCC driver then calls the assembler to work on that software.s that has been produced by the C compiler. The assembler produces an object file software.o. The GCC driver then invokes the linker LD. The LD linker takes the object file software.o and the C library libc.a, which is just a set of pre-compiled object file, pre-compiled and pre-assembled object files. That is what essentially a library is. So the linker is effectively taking a set of object files and then finally producing the binary. That is the output that you see on your subdirectories, in your folder. That is the output of the GCC compiler driver. But the compiler driver is internally actually calling this true C compiler, the target assembler, and the linker system. All right. This is what is happening in the forward direction. Why is so this set of tools, the CC1, assembler, LD, this is called as a tool chain, and the GCC driver is really just invoking a chain of tools internally. Okay. Why is this kind of a view done? Why do you really have a tool chain? So here is the idea. The core idea is, of course, you do not want to reinvent the wheel. All right, which is why people write software that provides various services, and that software, those services have been standardized into an API. You also have a language ecosystem. So, for example, if you take a language like Java or Python, you will have, or even C, for instance, or C++, you will have standard C library with a plethora of functions. You'll have the standard STL, you'll have the Java and Python packages ecosystem. That language API is also there. You also have software that has been written beforehand for various services. Let's actually go through them. So services API would be application APIs like Facebook, languages API like, say, for example, import XYZ that you might have in Python. Okay. Services API like email service, web service, system libraries like the math library, and of course the operating system kernels. So through your programs, you would like to duplicate your process through fork, or call another program and convert it into a process through exec. So a combination of fork and exec, whatever it may be, but these are various aspects of software production that we need. And the entire toolchain is constructed because it helps us to develop all of these things systematically. In particular, you write a piece of software and compile it into and assemble it into a set of object files and create libraries. That's one ways which is typically popular on GNU, Unix-like systems like GNU Linux. And on these systems, therefore, linking is sufficient in most cases. Okay. This is one of the reasons why we go into this idea of tool chains. Let's peel the onion a little more. Let's peel the onion a little more and look at the phases of the C compiler. Okay. So here is the scenario. The CC1 is the true C compiler that I'm talking about. It's going to take a C program as its input. It will typically do scanning and parsing. There'll be some machine independent optimizations. It will generate some target code. Then there'll be target specific optimizations, and then the target assembly code will be generated. All of these will be within the C compiler, and all that we as users would see would be the C program is converted to an assembly program. So, for instance, if you have one single file, f1.c, then it goes through the C compiler, creates f1.s, goes through the target assembler, and appears as f1.o. There is a certain reason why we want to have a C compiler or the GCC driver in the toolchain system like this. One, we already saw that this helps us in constructing software at various levels. Right. We would want to do that because it allows us. How do you create, say, for example, email API or, for that matter, networking API? For some of you, or if you are familiar with the way Unix Unisys implement this, you have an idea called as a socket. And there is a library of functions that are implemented that give you the socket interface. And as a programmer, all you do really is include some header files, and then there is a sequence in which you invoke some functions to create, initialize, use, and destroy socket connections. How is this possible? Is because your tool chain allows you to construct object files at various points and use them later at later points through linkers. So that's one side why you have a division between assemblers and linkers. Why is there the idea of an object file? But then the things don't stop there. What you are seeing right now in front of you is your compiler compiling just one program. All right. But that's not what is used in practice. In practice, you would actually want something more. Okay, I am going with something more happening. All right. In practice, you would want to actually use multiple files. We will come to that. But let's look at, if we have just one program, how the things progress. So I'm going to just take a quick, simple hello world program. For concreteness, the operating system is GNU Linux, but the ideas are same for other OSs. There are some differences in detail. The devil always is in the detail. Okay. Again, for concreteness, assume that there is some x86 assembly programming and x86 based architecture that is there. You don't have to know assembly programming as long as you see that whatever examples you're going to see, there is some amount of assembly that you can make reasonable sense of. That should suffice. Our typical cycle is edit, compile, execute. That is how we typically work. Let's spend a few minutes looking at this particular scenario where we are going to write some program as typical programmers. I am doing this because to ensure that everybody is on the same page. Not everyone may be using Unix and Linux machines. Just to give an idea about how things would be there, this is why we are writing this program. If you are used to using Windows programs, then you'll have to adapt this accordingly. But this example is indicative enough. That's one of the reasons why I'm doing this. So just have a look at this particular thing. You have finished editing, and then you use GCC, excuse me, and compile it. To compile that prog.c to a binary called myprog. Fortunately, GCC has been successful, and then you execute myprog. Well, it says hello world, great. By the way, that minus WALL argument of GCC is to enable all warnings. Here is the program read ELF that suddenly gave a lot of output. That's an oops, just ignore that. Let me now take the read ELF and do it step by step, one page at a time. You can see that there is a lot of output which describes the structure of the binary. It describes the structure of the binary. Right. You could see that some of the stuff that you had possibly written out is visible, but otherwise there is a whole lot of information there. And it may be there for whatever reason. All right. So here is the assembly version of the program, only a part of it though. You can see that there are some instructions and some arguments and so on and so forth. The line starts with a offset 0148, and after the offset you have the binary version of the instruction 5548 89E54883 EC10 and so on and so forth. Then in the third column onwards, you have the assembly code, push RB, push %RBP, move %RSP, %RBP, and so on and so forth. This is how the assembly version of your C program looks like. Okay. Now let's look at this problem. The tool chain and the assembly part has to be designed such that multiple source files can, it should be possible for programmers to write one single program, but spread across multiple source files. See, the programs in practice are extremely large, and dividing them into files allows organization, or allows people to organize their programs much better. Typically, for instance, you might have one file dedicated to one piece of the program, focusing on one piece. That is why it's very useful to have multiple files, one program spread across multiple files. Right. Now, how does the tool chain actually operate? So F1.c goes to the compiler and the assembler to get F1.o, F2.c goes to the same process to get F2.o, and so on and so forth up till F6.o. And just for concreteness, assuming that there are 6 files. What, for example, could be happening? So consider a scenario like this, that F1.c defines a variable, say integer a, and F2.c wants to use that variable. So the C language tells us that in F2.c you should tell the compiler that a is external to it. Extern a should be told in F2.c. So when the C compiler is going to compile f2.c, it must record that f2.c is going to use some variable a, but its actual definition is not known. That must be recorded by the C compiler in f2.s and continued by ahead by the target assembler in f2.o. Let me repeat that. f2.c contains the use of the variable a, but the definition of the variable is somewhere else. How is it known that it's somewhere else? Because as a programmer, you must declare it as external in f2.c. All right. These are the rules of the language that have been created so that you can do multiple source files, but there is a reason behind that. Note that according to our earlier understanding, we need to create a binary that is going to be working on the hardware platform. So our real purpose is all of these tool chains must eventually combine and give rise to one single memory, one single variable A. Okay, that is what must eventually happen. But until that eventual final happen, union occurs, each file must independently maintain that information. What does it have defined and what is it that has not been defined? That must be maintained in the object files. In fact, they are object files precisely because not everything is guaranteed to be defined. Otherwise, most of it is actually binary code. Consider this scenario. Suppose the program calls printf or maybe putf. All right. If you look at the source code, even if you look at the hello world source code, it just uses printf. But it never defines the printf function. Your source code does not really have printf definition at all. So how does this call work? This is where you can now look at the read ELF output of your program and you will see that there are some names which are undefined. For example, puts over here is undefined. All right. The binary for this codes for these names is unknown. Now let's have the C library. The C library actually has the code for say puts, printf, and many other fellows. If I take both of these together and now I create my prog, then my prog, the binary will contain both the program code and the printf code. And now it will be possible to run my prog program. This is called as linking. All right. The undefined objects in prog-o, puts and printf, are defined in libc.a. So if we combine them together, then it's possible to resolve the undefined objects in prog.o. That is how you will get the binary myprog. There is further thing that the linker does apart from this very important part of linking. Taking the C language specifically, you need to set up the activation of main. Note that in the C language, the main is just another function, except that that is the function where the C program actually starts from. Otherwise, main is just any other function. So just like any function has to be activated, main also must be activated. This activation of main is actually predefined in a library called or an object file called as CRT, C runtime.o. All right. We are going to assume that the stack segment has been allocated. But now the caller part of the activation must be set up. How do you do that? How do you think about this? You imagine that the OS is a C program calling a C function called main, which means that the OS has to set up the activation of main, and OS is the caller. Okay. Fortunately, the parameters of main are predefined and very well known, argc and argv. So it's possible for the operating system to construct the caller part of the activation very well. What is the caller part of the activation? We will see in this first or second session. Another thing that linker does, it sets the entry point and notes it in the ELF. The ELF is, by the way, the format of the executable file that is used on GNU Linux systems. Okay. What is meant by the entry point? The instruction from where the CPU is made to point to and begin execution. So here is a quick question. Given a C program, you know that it is supposed to start from main. What do you think should be the first sequence of machine instructions that should be executed? In other words, what do you think should be the entry point of all of this business? Okay. The entry point idea is a binary low level idea. Okay. Or put it another way, we are interested in the entry point in the binary version of the code. The C entry point we already know. The C entry point is a main function. Okay. Now let's look at the execution cycle. What happens when we execute? We did edit, we did compile, and let's look at execute. myprog. That is how you start executing it. What is it that must be done from an OS point of view? Well, the OS should be reading information from the binary, create the process control block entry, allocate the primary memory, etc., load and schedule it. Okay, that's to quickly read off whatever is there on the slide. But let's sort of see what we mean by reading the reading info from the ELF file. What is the information in the execute ELF file? There is, of course, the header, which describes how the rest of the file has been constructed. Okay. So it has information about number of segments, where does each segment start, how long is it, what are the various sets of symbols, defined and undefined. Okay. Here is the code segment. Code segments are also called as text segments, which typically have machine code instructions. You have data segments, which contain the binary versions of your variables in C program, and other information like symbol tables and so on and so forth. A symbol table is essentially the association between the symbol and the memory address that it has been given by the compiler. That's loosely speaking, that's how one can think of it like that. All right. The user just types in /myprog. The shell takes that. Okay. It scans the command line, forks and execs. That's what the shell does. All right. What does the forks do? What in response? What does the Unix kernel do for a fork? It duplicates the shell process. All right, and then execs the new myprog program over the forked shell process. So what do you mean by fork? It duplicates the shell process, and on the duplicated shell, it overwrites the duplicated shell with the myprog binary. All right. What does forking really do? First and foremost, it allocates primary memory for the fork shell, and then it duplicates the process control block entry. All right. So the process control block is over here. The shell entry in the process control block is over here. This is the shell process, and there is code, data, and stack, just pictorial, just illustrated. Okay. When you allocate primary memory for the fork shell, you're having a separate memory for the fork shell that is created, and you duplicate the process control block entry. So whatever was there in the process control block for the fork for the earlier process is now copied into another block by the fork call, duplicating it. So now you have a duplicate shell. Note, we will note that the scheduler is programmed to use the entries in the process control block. Okay. At this point, let's look at the exec side. Program from ELF, that is the binary of the program myprog. So let's assume that this is how myprog is there. I'm showing some slides over here of the myprog binary. Excuse me. So this is read from the primary memory. And now in the new duplicated shell, you resize the shell segments of that so that they correspond to what is there in the myprog binary. You load it from the ELF. I'm showing the ELF as if it loaded in the primary memory simply because, well, that is the truth. Although, I mean, you need to read the ELF to just figure out what are the contents in what way they are. All right. So it's just a matter of copying some piece of information the primary area to the actual process primary area. With the updated size segments and so updated entry point definitions, you now update the PCB data for the new shell. Note that color has been changed a little bit about that particular process control block entry. And now you have your new process myprog available for running. Whenever the scheduler picks it up from the process control block, your myprog dot will start executing. All right. How am I doing on time? It's 10 o'clock. Any questions before I continue?
Yes, sir.
Yeah, go ahead.
Back when we were talking about multiple source files and multiple object files, and you were referring to the linker finding out where the absolute positions are. Are you actually talking about a specific instance of relocation?
This one.
Yeah.
Okay. So
are you? My question is: are you talking about a specific instance or a specific example of how relocation works, or is this separate from relocation?
No, relocation is not separate. Relocation is implicit over here. Right. I did not describe relocation because I really did not describe the linking process.
Right. So yeah, that's exactly my question. So this is something that happens even before all that happens, or
no. So let's take up this example. All right. Let's start from the point where prog.o. So my prog that you see below, think of it as a memory area within which you want to construct the my prog binary. Okay. All right.
Yeah.
So Let's imagine that the MyProg memory area starts from the left and increases towards the right. Now, first, you are going to pick up the prog.o binary and put it in the initial part of MyProg area.
Okay.
All right. Let's say that prog.o occupies some k bytes. From 0 to k minus 1 from beginning of MyProg is what is occupied by prog.o. Fair enough?
Yeah.
The first step of linking is to just take the, let's say that the code of puts is required. So from the libc.au, extract the puts code and add it, concatenate it in myprog.o, myprog binary. So you place the puts code starting from k up to whatever is required by puts.
Right.
All right. Is that fair enough?
Yeah.
Is the picture clear?
Yeah.
So first k 0 to k minus 1 locations are used by prog.o, and k onwards you have puts.
Okay.
All right. Now, when somewhere in the prog.o you have a call to puts, right? Why did prog.o fail? Because the address to call where puts was not known when prog.o was being constructed. All right. So you can think of that. Suppose there is a call instruction towards puts, then the call instruction should have some kind of an address where it should jump to. That address will be blank. But now when you have in myprog, when you have prog.o and puts together, you also know that puts is at k. Therefore, the address of puts is known. The linker can now link. It can see that the call that was earlier undefined can now be defined. So now the linker will actually put the value k as an argument to call. All right. That is how the linking will take place. But now there is one more step to be done. When puts binary is going to be created, the entire code would assume that it is starting at memory location 0. So whatever processing the puts code is going to do, it's going to assume the addresses are starting from 0. But that is not the case now. The addresses actually start from k. So that address picks up, or in some sense relocation has to be done now before the myprog can be a legitimate complete binary. All right. So this relocation that I'm talking about here is more about fixing memory addresses. The term relocation is also used primarily from a point of view of memory management, where it's assumed that the memory where it's assumed that the program myprog.e is in virtual memory is laid out from memory location 0, and the operating system uses the relocation register to shift that address to somewhere in the other place in the primary memory. That is another way the word relocation is used. That second kind of a relocation is occurring in our memory management system, and that is not what I am referring to here. Over here, the only thing when I say relocation, what I really mean is address fixing. Okay. Does that clear the idea what you want to really think about, what you really want to ask?
Yes, that is precisely my question.
Okay,
Thank you.
all right. Any other question? Ooh, sorry. Any other question? So I'm coming towards relatively to the end of the session. The key idea that I want to discuss over here is this, that we need to construct according to the needs of the underlying machine. We have seen this particular key idea illustrated through a set of through a concrete set of example, through a concrete view. We took a x86 like machine with a MMU support. Why x86? Well, that's because that's typically the desktop. Maybe, well, I mean, I don't have much other time, but it would be interesting to see how an Android system would really look at this. I've also seen a concrete example in terms of a GNU Linux OS using the ELF format. All right. If I were to generalize it, then there are many possibilities. Like you could have different hardware and or different operating systems. Okay, the underlying machine could be a virtual machine instead of a hardware. Typically, virtual machines operate with bytecode. For example, the JVM Java virtual machine. Okay, or when I say virtual machine, I really sort of expand it to a level, to a very different level. I mean, virtual machines can not be low level virtual machines like JVM. They can even be very high level fellows, which effectively are the interpreters of your some of the high level languages. So when we say underlying machine, we can really generalize it. Not only we can have concrete hardware, but we can also think of virtual machines. Okay, but whatever it is, we need to construct the binaries according to the needs of the underlying machine. That is the key message, key understanding of this session. If there is anything that you need to take, that I am hoping you would take from this session, it is this idea. Here are some questions for you to sort of worry about, maybe throughout the day or throughout the week or even later. Okay. ELF is an executable file format on GNU Linux systems. You might want to find out what is the executable file format on your particular system or even other systems, maybe Windows or Mac or Android or whatever they are. All right. If there's any abbreviation, expand it. You can view your executable file format as a layouts data structure. So find out the details of this layout data structure and express it either as C structure or C++ classes. This is a slightly, I mean, it's not only information gathering, but it's slightly a little kind of an applied part where you want to sort of express it as C structures or C++ classes. In principle, you could use other languages, but I would suggest you just stick to these two. Other sets of questions which are difficult to discover, explore, study questions are these. How is the ELF format able to deal with both object and executable files? All right. The underlying unsaid part here is that probably object file formats and executable formats should be different. But hey, here is ELF that can do both. All right. So when you want to answer this question, you would want to contrast it. I mean, why is it that typically object file and executable file formats have been different, and why is ELF able to deal with both of them? Another exercise that you can try out is this: write a C program that would print the header information out of an ELF file, and because ELF can deal with object or executable, whatever may be given to your program, an object file or an ELF file, your program should print the corresponding header information. Okay. The last is a very concrete programming exercise, and it's something that builds up on most of the previous questions. These are some of the exercises that I suggest as a part of this session for your afternoon part, the lab sessions. Maybe whether you have them tomorrow or whenever they are scheduled. This is one. These are some sets of questions and exercises that I would want you to attempt during that time. Okay, so the summary of this session is this: high-level languages offer some useful models of programming. Oh God, this is a mess. This is actually the session summary of the next part. I am so sorry. Let me skip that, but I'll give you the session summary in a different way. What we really did was to understand what is it that the hardware gives us. This gave us a concrete goal. This is what we want our binary to be. Then we studied our typical program development process, where we saw what really is a tool chain. We saw what does the tool chain really do, and how does it actually give us the binary in a way that the hardware expects. Along the way, we saw the roles of many fellows. For instance, we saw the compiler being separated from the assembler. The compiler was a target independent entity that generated a target specific code. Assemblers are always going to be target specific. They just take up the assembler file and generate an object code. Why do we distinguish between object code and the binary executable? Because object code idea allows us to split our programs into individual manageable units. We use the linker tool to combine all of the manageable units together into a binary. The linker not only does that, but it also establishes the entry point, the point where the fellow should start. Your binary should start executing when it gets scheduled. All right, that is the first instruction that it should start with. Why does the linker state that? Because that information is used by the operating system when it loads the program and sets up the instruction pointer register to the first instruction that the binary must execute. That is how all of the things come together, the hardware and the software. And along the way, we have seen some parts that are occurring. For example, the linker was also setting up the C runtime system. What was the C runtime system? The C language expected main to be a usual function with two predefined, well-defined arguments: integer argc and character pointer array argv. Setting up access to these arguments was something that the linker set up. This was a requirement from a runtime execution point of view. Okay. So there are some issues that we still now need to consider, but now we understand why we need runtime. There are some aspects that are not known by the compilation system, the entire tool chain, and have to be addressed by the runtime. But we also understand that the compilation, the entire tool chain can prepare the runtime. This is what we will see in the next session. Thank you guys for your attention.